My wonderful students, friends, Romans, and countrymen, lend me your ears. Couple things to talk about. First of all, is there anybody in here that it's your birthday today or over the weekend? Raise your hand if it was your birthday. Anybody else? What? Okay. Let's sing happy birthday for these guys. Happy birthday to you. Happy birthday to you. Happy birthday, happy birthday, happy birthday to both of you. Yay! All right. Now that cheered me up. Good. Because we're going to need cheering up because exam 2's coming. And so stopping time, stopping distance. Yep. We're going to have a ton of stuff. But you know what that means? It means, you see, because you can only have a certain, 2 or 3 calculations max, other than the cinchy ones that we have on multiple choice. But, 2 or 3 max in clicking. So even though, we've got angular momentum, we've got stopping time, we got all this other stuff, momentum, boxcars, I can only give you 2 or 3 of those. But you're still going to, still a lot of stuff to get ready for. Also, before we get any further, let me mention you're going to have some homework tonight in web courses. It'll be homework 11. And it won't be a gigantic one, but it will be due on Thursday morning at 10:30, the way that they normally are. Do not be caught napping. Also, I have activated mini review, Chapter 4 mini review in the Great Rivers website. All right, and has anybody in here already taken it once? Anybody? Bueller? Nobody? Okay. Somebody in the first hour had, so that's good. So that's running. And hey, could somebody actually check that right now in the Great Rivers? Put down your Chick-fil-A and check the Great River. Do that real quick and see if you can get to Chapter 4. Now, Chapter 5 mini review, we're going to be ready for it on Thursday. So that'll run Thursday to Tuesday, in other words, over the weekend. So we're going to have 3, 4, and 5 mini reviews, okay, as study tools, plus homework 11. And then you're going to have homework 12 from Thursday. I'll assign that on Thursday until Tuesday. So you got a ton of homework. We didn't have any this weekend, but we're going to have a ton this week and getting ready for exam 2. All right, questions about that? Welcome, rejoice, and come in. Anybody get into the Great Rivers Chapter 4 mini review? Please, somebody try it. Real quick like. The first person that can do it will not get any bonus points, but you'll make me. Anybody do it yet? Anybody get in Chapter 4 mini review? The reason, is it working? You were just you're faking me out. It's a 5-yard penalty. Illegal procedure. False start. Anyways, you can raise your hand if you do that a little bit later. You got it? Okay, good. Thank you for doing that. The reason I have to ask is because my account does not work the same way your guys' accounts do. So I'm not used to it yet. This is the first semester we've been doing it, so eventually I'll know a little bit more without even thinking how it works. Last time we talked about this concept of angular momentum and torque, and we're going to go into that because what we want to do is, figure out. So, for instance, this young lady that's at the Olympics ice skating, you can tell she's spinning. I mean, it's a stop photo. It's an action photo. It stops the action, but her skirt's kind of flying out, and actually her hair is flying out into the universe as well. So you can tell that she's actually spinning. And she's got her hands in really tight, so she's really spinning fast in this photo. Now, what is it that can change the angular momentum state of a given object, like an ice skater or a planet or an asteroid? Say there's an asteroid heading for Earth and it's spinning. Or say that it's heading directly towards Earth and we want to give it some angular momentum so that it assumes a circular orbit and loops around the Earth. So we got guys studying that, trying to develop tools, a big, huge spacecraft to actually tow an asteroid out of harm's way. In the movies and stuff, they just they send Bruce Willis up there and he nukes it or whatever. But in real life, they're going to try not to do that. So we want to know about angular momentum state. Here's how you do it: leverage, torque. This business of being on like this picture from the textbook used to be page 64. It's in chapter 5 now somewhere. And we're going to talk about this today. But before we do, I have a few iClicker items to start with you. Get your clicker going. Frequency DD. Oh, man. And let's do some clicking activity. And what we're going to try to do. Have you got Chick-fil-A back there too? And it's some students over here with Chick-fil-A in the second row. They're driving me crazy. Tell you. But let's talk about seesaws. All right. So here's your first question. Read it carefully. Look at the diagram carefully. Make an answer. And hopefully get your clicker going. $20 seconds. I see people going like this and like this. That's good. It's nice. They're talking to their neighbor and stuff. It's good. I like seeing it because it means you're thinking. Thinking with your hands. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. 196 students. This one's going to go clockwise because the heavier mass is over on the right. So that side's going to go down. The left side's going to go up. So it's clockwise. Okay, that's pretty cinchy. What about this one? Question number 2. If you dare. You know, a few years ago, one of my students, she sat in the front row in another lecture hall. Every day, she would bring a little bag, fun-sized bag of Cheetos or Doritos, and she would open it up right in the middle of class. And it was always a it's like, hypnosis almost. She became a TA. She became an SI leader before Maria. She was a good student, but she always did that just to give me the business. Tell you. All right, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, you guys, get those answers in. All right. This one's, most of you got it correct. This one is going to balance. It has equal force downward on the right and equal force downward on the left. And they're the same distance apart. Now, if you change the distance for one of them, then you're going to get some spin, either clockwise or counterclockwise, depending on which one you bring in closer. All right, so this is the kind of thing that we're going to study today. Now, here's another diagram from the textbook. At equal positions, my son defeats his little sister because he is heavier. Equal positions, the heavier one wins. Yeah, the sun creates more torque about point P. Now, we're going to be talking about torque and angular momentum and moment of inertia today. So let's get down to business. Torque is the angular analog, the rotational analog of force. It depends on, your position and how much leverage you put on it. Like this big wrench here. This crescent wrench. And it's obviously a left-handed crescent wrench. And I've seen guys in physics labs with big, wrenches, a big crescent wrench like this big, really stout, for these big pipes, and break it. I've seen them break it and shatter it. They put too much torque on it. The steel couldn't hold it up. Steel will break if you're putting too much. It's a famous incident in the lab because he had this big wrench, and then he took a big pipe and he put it on the end of the wrench, and then he got to the end of the pipe, and then he really had a lot of leverage, a lot of torque. So he was on the seesaw way out there. So he could and so he ended up breaking the wrenches. So here's an example, another diagram from the textbook. You apply force F1 upward, and the hinge is over here. Let me get my cursor. Come on, baby. All right, so here's your hinge over here at point H on the right side of the door, kind of like this door over here at the exit. Okay, the hinge is on the right. The push plate, the hand plate's on the left. All right. And that's what this guy's doing, F1. He's pushing there. Now, he's going to get the door to open. This guy down here with force F2 pushing straight toward the hinge, along the door, he's going to be there till the cows come home. And the door's not going to go in. He might be able to, if he was pulling the door the opposite direction, he might be able to rip it off its hinges, like Arnold or something. But, the door's not going to spin. But the guy up on top, he's got maximum torque. All right, he's as far away from the hinge as he can. He's as far out on the seesaw as he can get. And then he's applying his force. Now, if he was in here, like halfway, then he'd apply some torque. And still pushing upward, he'd be getting some torque, but not maximum torque. The maximum torque is right out here. And instinctively to do that, If you can't reach, if you're carrying a bunch of stuff in from the grocery store and you can't reach it all the way to the far side of the door, you can still get it if you push over here in the middle. But you like to do it out here. Now this guy, 0 torque. And there's all kinds of trig. If we were going to use trig in this class, we would do, a bunch of trig and, but for us, it's important to remember that perpendicular to the door, maximum torque, parallel or anti-parallel to the door, in other words, into the hinge or away from the hinge, no torque. It won't spin the door. You might rip it off its hinges, but you're not going to open it or close it. Now here's a combination and some vocabulary terms I want you to study and have these ready. Translational, rotational, and combination motion of both. Translational motion, that means from point A to point B, from here to Miami. From here over to the student union. You have a speed, you have a direction, you get there in a certain amount of time. Rotational, you have some speed. Every part of your object that's spinning is going to have some meters per second of speed, but it ain't going anywhere. If it's spinning, that door, no matter how many meters per second of speed you give it, it's not going to leave the building. It's just going to return, it might spin on its axis. When I was a little kid, we had, I wonder if they probably, most of you guys probably weren't even allowed to play on the playground. But back when I was a kid, we had to walk uphill to school in the snow, both ways, 2 miles, And we had this playground ride, I guess, playground thing, and it was just a gate. It was an iron post embedded in cement in the ground, and then on the iron or steel post, on the steel post was a gate. So about this wide, painted red, and it had a little ledge that you could stand on. But if you got and it had a little bar that you could hold on to. So you stand on the ledge, and you hold on to the bar, and you're like in first grade or second grade, so you're like a little shrimpy kid, And so you're holding on to the bar, and you go around a circle, have a nice time. But what we used to do is you would get your buddies to spin so fast that you hold on to the bar and you let your feet go and you were flying. That's what we used to do. That little gate, that was pretty good. So that's really spinning if you're going that fast. You guys probably never had any cool stuff in the playground like that. Not anymore. You just guys had phones and stuff, and had to be supervised by your mom and everything. Man, we used to leave home in the morning and not come home until dinner time. You couldn't do that today without an Amber Alert. Man, I tell you. I shouldn't make a joke. Amber Alert's a serious thing. Anyway, as I said, the rotational analog of F equals ma is torque, except, and here's F equals ma. F net equals delta P over delta T. We've seen that before. Now, what we want to do is change an angular momentum state. So the torque and the Greek letter tau, lowercase tau, is one of the customary symbols for torque. You see other symbols, but that's the one that I'm going to use. It's going to be delta something over delta T. And the something in the numerator is angular momentum that we've already alluded to, ice skater momentum. The spin momentum. In fact, there's 2 different kinds of angular momentum. And it's important to distinguish between the 2 kinds. There's orbital angular momentum, which you have if you're on a path around a central point, like a planet going around the sun, or an atom going around a nucleus, or an electron going around a nucleus. And then there's something called spin angular momentum. Now the Earth and most of the planets have spin angular momentum. Earth's got a little bit of RPMs. One rotation per day, let's see, 24 hours times 60. So one spin, what's 24 times 60? 24 times 60. 120, 4 times 1440. Okay, so 14. So one spin every 1440 minutes for Earth, which, okay, do 1 over 1440. What do you get? That's like 0.000 something. It'd be about a 0.007. Yeah, okay. So 0.00069 blah 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 RPMs for Earth. So Earth has spin angular momentum, and it's also going around the sun. It has orbital angular momentum. And for that one, the orbital rate is once every 365 days. It's a huge orbit. And Earth is really rotating on the orbit. But yeah, you have to distinguish between both. And by the way, raise your hand if you've ever had chemistry class here at UCF. Raise your hand. A few of yous? Okay. And some of you probably will take a chemistry class or something along the way. And one of the things that they teach in chemistry class is how in the periodic table, the orbital shape of electrons, they have this weird, like dumbbell shape and, 8-sided dumbbells and sometimes a spherical shape. That's all angular momentum states that distinguish those shapes. So it's definitely something to keep track of. All right, let's focus in on orbital. All right, so what you want to do with orbital angular momentum is you want to figure out some fixed point of interest around which you're moving. And you could actually be moving in a straight line. I mean, you still have an angular, it should be changing. The angular momentum would be changing. But a circular, like the Earth is on a circular, and it's an elliptical path, but it's so close to a perfect circle. It's kind of hard to tell the Earth's orbit around the sun apart from a perfect circle. So you have to have some fixed point of interest. So here's like the Earth going around the sun, and the sun is that green sphere down in the lower right. And did you know that the dominant color, the brightest color, the sunlight, red, orange, yellow, green, blue, indigo, violet, those colors, the brightest is green, right in the middle of the spectrum. So that's why I always make the sun green. You could have something on an elliptical orbit, kind of an oblong orbit like a comet. And we'll do a little analysis of a comet's orbit here in a minute. And you also have to have some kind of distance and angle from that point out, so from the sun out to the planet. Okay, so you have you have for the Earth, position vector r, that's that black line. But, it might be going out to the electron orbiting a nucleus. So an electron orbiting a proton, that's a hydrogen atom. And we know all about those hydrogens. It's one of the few atoms we really know well. And then you also have to factor in the velocity of the object. So where is it and what direction is it going on its orbit? Now, go ahead and pencil in down here in the lower right a velocity vector v in red that I've got. And this one is in this orbit for the Earth, it's going counterclockwise in this perspective. Right? So make a note, this is from a vantage point to the north of the solar system. All the planets orbit on this pretty close to the same plane. So the solar system is like a dish if you only think about the planets and the sun. And north of it, towards the North Star, is where we're looking at it. So we're off a little bit to the side and a little bit north, and we're looking down. And hey, you guys, all the planets travel counterclockwise when you look from the North Star. You look at you go out towards the North Star a little bit, and you look back at the solar system and you watch them. Yeah, they're going in counterclockwise orbits. A lot of comets, the asteroid belt. Now, the asteroid belt is kind of chaotic sometimes, so there's things dipping in and out of it. But the general sense of the asteroid belt is also counterclockwise. Most moons, but not all of them, but most moons around the planets, the planet Jupiter, Saturn, the rings of Saturn, counterclockwise. Although the rings of Saturn, they're tilted a little bit with respect to the main plane of the solar system. But now comets come in from all different directions. But there's a belt of comets called the Kuiper belt. And it's out past Pluto. And actually, Pluto's on the inner edge of the Kuiper belt. And those comets are all in the same plane, and most of them are counterclockwise orbits as well. Halley's Comet, counterclockwise. So the position vector R, so here's the formula. On a circular orbit, it's really cinchy. L equals mRV. The angular momentum, capital L is one of the customary symbols you see. Sometimes you see capital J. Sometimes you see capital S especially if it's a spin angular momentum. And it's just if it's on a circular orbit, it's particularly easy. It's just mRV. Mass times the radius of the orbit times the orbital speed. And the thing is, the centripetal force of gravity on a circular orbit is going to be constant if you're on a circular path. Same distance away from the sun, same newtons of force all the way through, centripetal force, same speed. So it's uniform circular motion. Everything's copacetic. So V is always perpendicular to the radius position vector here, just like what I have in this diagram. But it's not always the case. But you always have to factor in the geometry of the position vector R and the velocity vector V. Now we're going to do an overhead view now of a comet. All right, like the one that I've got pictured in red here. So let's go to the next screen and go ahead and make yourself a picture. Try to make it the same proportions. And you can see down here, A and B are my two proportions for the comet. It's half of its width is 400 pixels. Half of its height is 240 pixels. Now, all you got to do is draw something about this proportion and then draw the center lines, the symmetry lines. And then the sun is out here at one of the foci, one of the focus points. Every ellipse has one to the left and one to the right. And I've sketched in my comet kind of up here. It's not on one of the axes. It's not out at the furthest point, aphelion. It's just kind of some generic point up here in the first quadrant. Here's the sun down here. That's at one of the focus points. Point of closest approach, perihelion. Above the sun, the point closest above the sun. So when you're right floating above the sun, you're at perihelion. Gravity is stronger there, you're really whipping fast. Second important point, aphelion. And we've got spacecraft orbiting the sun. We've got a few. So they're going to have an aphelion and a perihelion. And comets are definitely, there's a lot of them that look like this. Okay. So now, as I mentioned, the position and the velocity vectors are what make the difference. So let's draw in now the position vector. Here it is, from the sun out to the comet. So go ahead and draw an arrow out there as I have done. And then let's say that this comet is going clockwise in this view. So its velocity vector tangent to the ellipse and kind of down and to the right a little bit as I have sketched mine. All right. And if you're trying to figure out the angular momentum for a comet like this on an elliptical orbit, you got to use trig. All right. Now, we're not going to use trig in this class, but I mean, this is, you can see that, Laura, you can see that those two vectors, they meet at a sharp acute angle. Okay, they're not perpendicular. Circular orbit, perpendicular, all 24/7, easy. But this one you get, so, this is what you'd have to, hack using trig and a bunch of calculus and stuff, which we're not going to do. It's challenging for a grad student to do that. I mean, but there it is. I mean, it's a picture of it. But for us, we're going to focus on circular orbits because they're a walk in the park. Because there's no perihelion or aphelion. It's the same distance, Sidora, all the way through, on a circular. If it's a circular orbit, every point is aphelion, every point is perihelion. You can think of it that way. All right. So on a circular path, the velocity vector is always perpendicular to the position vector. Okay, and so when that's the case, L equals MRV, just multiply them together. And that's all you need to do. And then, but angular momentum is a vector. And I'm going to show you something called the right-hand rule towards the end of class that will help you figure out the direction. And so this is how you figure out the size. Orbital angular momentum, L equals MRV, and then right-hand rule, end of class, gives you the direction of it. Right now, spin angular momentum. Let's look at something like this. A disk spinning on an axis or an axle. And this diagram's got 600 RPM. So it's really going pretty fast. That's 10, let's see. 600 RPM is 10 per second. 10 spins per second. Now, the spin angular momentum is actually the sum of all the little MRVs of each pixel of that axle. So if you pixelate not the axle, if you pixelate the disk, square millimeter by square millimeter, pixel by pixel, and then do MRV for each of those and then add them up, you get a different formula, and it's actually related to the angular velocity omega. So make a note that the spin angular momentum, L, is something called I times omega, and I is known as the moment of inertia, and I'm going to show you how to calculate that in just a minute. Can you imagine all the calculations you're going to have to know how to do, at least basic ones, for exam 2? Oh my goodness. And so exam 2 is going to be a bear cat. Hopefully not too much of a bear cat, but I mean there's going to be, it's going to be a challenge just knowing all the stuff that you got to know. So spin is equal to moment of inertia times omega, lowercase omega. That's the spin rate. So 600 RPM in this diagram. That's omega. All right? And so so you may say to yourself, Dr. B, I thought it was every pixel with some MRV, and you just add them up. And my answer to you is yes. That is what it is. That if you think about it, MRV, every pixel has a V. Every pixel has an R. Okay? But the further out towards the rim or the edge of this disk, the faster you're going. V is fast out there. And R is big. Right now, the pixels down here close to the axle, they're moving. They have the same spin rate, everything's got 600 RPM in this diagram. But these pixels down here in close, they're going 600 RPM, but the meters per second is a little bit smaller because they're turning a smaller circle. All right? Every 600 times a minute, they make a small circle, whereas out here, 600 times a minute, they got to make a big circle. So these things are really whipping out here, and they're kind of a little bit they're still going pretty good, 600 RPM. You still got a lot of speed out here, but the closer you get to the axle, the smaller the speed, and the smaller the R is. So it's kind of tricky. Now, what we found is that there's this concept called moment of inertia, which is the rotational analog of mass. And that is what you would use to calculate spin angular momentum. Matter of fact, if you look at this, this is analogous to the definition of regular momentum. P equals mv. M is the mass of the object, v is its velocity. In this case, I is the rotational analog of mass, and omega is the rotational velocity, or the angular velocity. So it's very similar to that. Now, the exception of this is the electron. We don't really understand the intrinsic angular momentum of an electron. So we can think of the electron as having spin angular momentum, but we've never been able to see, you think of it as like a little bead spinning, or a little top spinning, but we've never been able to measure like the diameter of the top or the diameter of the bead. Electrons don't seem to have any fundamental structure. They just seem to exist. Photons the same. The photon has intrinsic spin as well. It's different from the electron. Now let's take a look at some more things here on this disk. Okay, now this picture shows omega up here, kind of towards the middle and at the top. With that kind of circular, so this one, it's kind of going this way, all right? So that would be clockwise or counterclockwise? That'd be counterclockwise, right. All right, so you got to always be ready to analyze, is it clockwise or counterclockwise? In this case, it's counterclockwise, right? So every point on that disk has the same angular velocity, all right? If it's rigid. Now, if it's not rigid, then you can still analyze it, but it's not as cinchy. 2 points at different distances from the axis of rotation will have different speeds, and so that is why you have to use this concept of moment of inertia, I, because that is the moment of inertia, as we shall see, is a property of the shape and distribution of mass. And the shape and distribution of mass of the seesaw or anything else, the door, will control its angular momentum and its spin state. So now I want to, before we continue, let me just draw your attention to some YouTubes. We've got a couple playlists. So outside of the 10:30 a.m. lecture playlist are a bunch of other playlists, and what I invite you to do is look at this one over here, for angular momentum. All right, there's a separate one, and we're going to try to do some demonstrations in class on Thursday using a bicycle wheel and a really nice little stool that is very low friction, and you'll see some cool effects, and I'll be asking you about those demonstrations. So make sure you're here on Thursday, and you'll be ready for exam 2. Exam 2, go for it. All right, now, torques. Let's talk about torques a little bit more. All right. We think of baseballs, as point objects, cannonballs and stuff. because they're rigid and they're spherical. But a real object, like this board, this plank, yeah, if you push, exert some newtons upward on this plank or across the pond on this plank, you're going to achieve different states of motion. So if you push like F1, it goes right through the center of mass of this plank. The plank is going to go straight up in this diagram. Okay, you're going to accelerate it for a second or two, and it's going to go straight, but it's not going to spin. All right? Because you're exerting a force on it, but at the center of mass. That's like pushing toward the hinge on this door up here. All right? So if the natural hinge or the natural spin axis of any object goes through its center of mass. So if you exert your force as if you're going through the center of mass, it's not going to spin. All right? Now, if you're over here with force 2, a few centimeters off to the left, you're going to give it some meters per second squared of acceleration because it's getting some newtons. All right? Some upward newtons. But it's also going to spin because you're on the seesaw. If you sit on a seesaw right at the center of the seesaw will it won't do anything. But as soon as you get off to the left or the right, it's going to spin. I mean, if you're the only person on there. All right, and that's what we got here. So you're going to have some motion depending on F equals ma, and you're going to have some torque effects. And you may actually have a combination of both. We're going to look at some cool pictures here in a second. So the distribution of matter makes a significant difference. And the distribution of matter is what we encode into the moment of inertia. All right, now the moment of inertia of this plank, we could calculate it in the manner that I'm going to show you. And we're not going to do a plank, but we could do it if we had to. It would involve some trig and some calculus and stuff. But let's take a look at a couple strobe photos. Now here's something that is a overhead picture of somebody sliding a crescent wrench from left to right and taking strobe photos of it. Pretty good quality too. Ooh, excuse me. Now you can see, if you look carefully, you'll see a little black kind of a plus sign or a diamond painted on this wrench. And so to help you see it, I made this set of light blue diamonds. So here, okay, so there's where that, all right? So here it is, all right? And if you look at those diamonds, they're equally spaced. They're horizontal. They're all going to the right, and they're equally spaced. So this thing is moving, the center of mass is moving at a constant velocity or pretty close to a constant velocity. All right? So make a note of that in this diagram. But what's not moving at a constant velocity is the rest of this wrench. It's spinning. All right? So this is an example of somebody that tossed a wrench with some F net horizontally, but slightly off center. All right, so that it gave it a little bit of spin. And if you're playing, when you're playing tennis or golf, in golf, do you put spin on the ball when you're hitting it? Is that ever anybody here is an ace at golf or good at golf? Everybody, you're from Florida and nobody plays golf? I guess I don't play golf, but do you put spin on it? Okay. Tennis, definitely. Ping pong, oh my goodness. Ping pong. Baseball, you put spin on something, you get that curveball action going. All right? So spin, golf spin, you can hook something around a tree, get it around on a curved path, throw a curveball. And it's by doing something like this. Look at this guy. Oh my goodness. Here's another. Can you imagine? This guy's up here. He takes off here. He's looking good. It's like he's going up a steep hill. And he lands over here. It's like he's coming down a steep hill. But in the middle, he does a backflip. So over here, he puts some torque. The ramp gives him a direction. All right? So if he doesn't do anything else, he's going to follow a parabolic arc. But he also, at the last instant, puts some torque on his bike, and he executes a backflip and gets... Now, it was explained to me that as dangerous as this looks, it's got to be dangerous. Can you imagine trying to practice this and you don't get it quite right? I mean, you're an inch or two off, that's it. You're going to break every bone in your body. And so we were talking about it in the 9 o'clock lecture. I see your hand. I'll get to you in a second. We were talking about it in the 9 o'clock, and a student came up after class. They said, Dr. B, I didn't want to say it in class, but what these guys do, when they're up in the air, they'll hit the throttle or hit the brakes. And you know why? Because if you hit the throttle, your drive wheel will increase its angular momentum. And that will control your overall spin, the spin of the entire bike. And same thing with the brakes. If you squeeze the brakes a little bit, you'll slow down the drive wheel or the front wheel. And so the student was saying, what they do is, as they go through this parabolic arc, they give it a little gas or hit the brake a little bit and make sure that they land properly. Can you imagine that? And you're in the middle of the air. I'd like totally lose my lunch. I shouldn't say I would, because I would never do it. But I mean, if I had to, if somebody, paid me $1 million, maybe I would try it. If the jump was like this far, 2 inches off the ground, maybe. But other than that, but that's what they do. So and you know what it's like? It's like in a rocket, like the shuttle astronauts and stuff. They put the throttles, when they're on their ascent stage, they'll throttle in and throttle out, to control the exact trajectory that they want. And apparently that's what these guys do. Did you have a question?
Yeah, I was wondering if you wanted me to demonstrate that.
You mean in class?
Yeah.
Right now?
Yeah.
Come on, yeah. Come down here.
I can go on the stage.
Yeah. Now when you practiced this, you were on mats and foam pits and stuff?
Yeah.
Now what team are you on? Okay. Cheer team. Now what are you going to do? Daniel Bieski. Wait a minute. He's not nitro. Because nitro is secret, right? So actually, nitro would never admit that he's a nitro. Have you ever seen Nitro do backflips? No. All right. He can't. Nitro can do backflips. Oh my goodness. Yep. Okay, Daniel.
Ready? Everyone got the chords in?
Sweet! Nice! Good job. Man, I tell you what. So he basically jumped in the air and his center mass went up and came down. You know, we should have measured where your feet were when you started and where your feet were when you landed. No, we'll do it again on Thursday. We'll do it again on Thursday. Yeah, I think that's because you jump straight up, but he gives himself enough torque on the way up. And Daniel, have you ever blown it? Huh? Yeah, so you can blow. If you don't do the right spin rate, your feet, you land on your, your feet will be out in front of you and you land right on your keister. Or the other way, your feet will be behind you and you land right on your face. All right, anyway, so good. Thank you for that backflip. Are you signing it? Okay. Good. All right, so let's calculate the moment of inertia. Here's the basic formula. It's the Greek letter sigma here. Uh-oh. I just lost my session. The Greek letter sigma here means summation. And what this means is add up the quantity mr squared for each pixel of the object that you're studying. So, for instance, these dumbbells, R is measured relative to the spin axis, right? So for these dumbbells, there's a vertical spin axis right through the middle of the dumbbell. All right, so the one on the left is 45 centimeters across. So 0.225 meters left, 0.225. So you have pixels, like 10 kilograms of pixels at 0.225 meters to the left, and you have 10 kilograms, 0.225 meters to the right for the first one. The second one, same 10 kilograms, but 0.30 meters to the left, and 10 kilograms, 0.30 meters to the right. So that distribution of mass is going to affect which one's easier to spin, to change the angular momentum for. So let me just try to sign in here. Hold on a second, you guys. My Bill Gates extravaganza here signed me out. Let me get back in here. So you guys have got 2 sessions today. The Bluebird of Happiness does not use Windows. Resume session. Okay, we will. I just have one. Hold on, let me see what we got here. All right. So this is what we're going to do. We're going to calculate a moment of inertia, not for a dumbbell, but it's for a simpler object. Once we do that, then you look up your RPMs. That's going to be your omega, so like 600 RPMs or whatever it happens to be. And then you multiply by the moment of inertia. So this mr squared, the sum of all the mr squareds for each pixel by pixel, is the rotational analog of the mass. All right, so let's do a simple calculation. All right, so go ahead and make a sketch, kind of a cinchy barbell, 7 kilograms each side, and let's say that it's pretty big, 4.2 meters between the centers of the 2 weights. Now we're going to ignore the bar. We're going to assume the bar is massless. Okay? In other words, that's a typical physics department shorthand. All right? And this is actually a model called the rigid rotator that we actually use this kind of a structure for figuring out atoms and molecules and stuff. So it's, all right? Now, draw your axis right through the middle, so down the symmetry. You know, you could do any axis you want. I mean, you could do an axis right along the barbell, you know, horizontal axis. You could do a vertical axis through one of the masses on the left or the right. Or you could do a vertical axis, you know, at the edge of the page to the left or the edge of the page to the right. You know, it's just but we're going to use this one. You know, it's up to you, whatever you want to do. All right? Now, relative to the axis, each pixel, it's a pretty big pixel, 7 kilograms. Each pixel's got 0.210 meters of R. So I can figure out mr squared for the one on the left and mr squared for the one on the right, and then add them together, sum them up. Letter sigma. All right, so here's my formula. Okay, and on the right, there's my structure. And here's our first step. 7 kilograms mass on the left times r squared, 2.10 meters, quantity squared. And then I've got another 7 kilograms on the right, and it's 2.10 meters, quantity squared. So when I say add up all the mr squareds, pixel by pixel, yeah, basically you're doing this. All right, so these are pretty big pixels, but it works. And it's good enough for government work. All right. And then 2.1, you get your calculators out, because you're going to have to do this in a second on iClicker. Anybody verify me 2.10 quantity squared 4.41? Okay. All right. And it's meters squared, square meters. Okay, so 7 times 4 is 28. So this is going to be a little bit bigger than 28. So this might be 29 or something. All right. And then we got another the same size, the second part. So what's 7 times 4.41? 30.87? Okay, that sounds about right. That's what I've got. All right, so we're summing them up. So that capital Greek sigma means add them up. Calculate mr squared for each pixel and then add them up. That's what that means. All right, so and we just have two masses. You know, something like a bicycle wheel, you know, it's a little fancier. A cube, a little fancier. Sphere, a little fancier, but I mean, you could do it. Got to use calculus and stuff. So your net moment of inertia for this axis and this object is 61.74 kilogram meters squared. Now notice that unit is a mass times a square of a distance. All right, that's moment of inertia. That is the that is the number that when you multiply it by the RPMs, you get an angular momentum. All right? So if you were to spin this thing, this dumbbell, about the vertical axis, you know, like 2 RPMs, you'd go 2 times 61.74, and that would give you your your angular momentum. All right, now we're going to do a calculation together, and you don't have to hit the refresh key because it's multiple choice. Here we go. Same kind of calculation. And just do it, but sketch it out and work it out carefully. I'll give you a minute or two. And hopefully you guys will crush this one. And just work it, you know, the sum of mr squareds. That's all you got to do. Mr squared and then another mr squared and then add them up. That was nice singing happy birthday. I like that. Thirty seconds. Ten, 9, 8, 7, 6, 5. What? Oh. Good? Okay. Good? Okay. Yeah, most of you guys got it right. 9.8. Here's the calculation in case you got tripped up. We're summing over 2 pixels, 2 masses, and they're each 2.5 kilograms, but slightly different distance, 1.40 meters, quantity squared. So that works out to 1.96 square meters. Multiply that by 2.5 and then do it again, and you get 9.8 kilogram meters squared. Now your homework tonight, you're going to have, I think I'll probably give you a couple, 3 problems, kind of cinchy, maybe one of these type problems. So the moment of inertia encodes this. The resistance to spinning up to a higher spin rate or spinning down to a lower spin rate. Right? Just as mass, inertial mass, encodes the resistance to us moving to a higher speed or a lower speed. The more mass you have, the tougher it is to speed up or slow down. Same thing with a moment of inertia. Now, a moment of inertia, you can have a certain mass and not very much moment of inertia. Or the same mass and a whole lot of moment of inertia. So let's try and let's look at some results for doing this MR squared business for some more complex shapes. Now your textbook is supposed to have this table, but apparently it's not in there. So I'm going to have to put it up in web courses again. I don't know why they don't put this table in there. Let's look at the first two. A thin hoop. Basically, that's a bunch of mass at the same radius away from the spin axis. All right, so the spin axis is going right through the middle of the hoop. And it's perpendicular to the plane of the hoop. All right, and so all the mass is at distance r. So when you do that summation, you can factor r squared outside the summation, and then you're just adding up the m's. So it works out to mr squared. Now if you do the same thing with a solid cylinder of the same radius and the same mass, you get this factor of 1/2 right here. Look at that. All right, same mass, same radius, but now you've got a 1/2. So you know that 1/2 encodes the different distribution of mass between a cylinder and a hoop that's the same diameter and radius and the same mass. So you're talking, like 1 kilogram hoop, 1 kilogram cylinder, half a meter radius for both, but they have different, one's easier to spin up. Which one's easier to spin up? The cylinder or the hoop? Cylinder is, because it's smaller. 1/2 mr squared. Check out the sphere. You do all the, and you got to do a lot of trig and calculus to do this. The sphere, you don't even get 1/2, you get 2/5. So the sphere is a total slacker. And why is that? Because it has a different distribution of matter. The hoop, it's all out there. There's nothing in the middle of the hoop. So it's got a lot of empty air. All kilograms of its mass are out at distance r. That's what makes it a hoop. Now the sphere, you don't have a hoop shape, you have a sphere shape, and so you got a lot of pixels of mass down close to the axis. So mr squared, pixel by pixel, is pretty small down there by the axis. And you do all the calculus and trig and stuff, which don't worry about it, but do worry about that 2/5. It comes out to 2/5. And for a stick of length L and the same mass, dude, you can think of that length as being the diameter. 1/12 ml squared. So for every fairly simple shape, pyramid, cube, dodecahedron, a cube, an oblong rectangle, an oblong brick. You can calculate mr squared fairly easily. You got to use calculus. But you're going to get a different factor out in front. And so there's going to be a factor of m, and one of the dimensions at least, quantity squared. So like for the sphere, m times the radius squared. And then a factor that could be 2/5 or some other factor depending on the shape. So this 2/5, it encodes the spherical distribution of mass. And down here, the 1/12, that encodes the stick's distribution of mass relative to that spin axis. Now, if you choose a different axis for the stick, you can't choose a different axis for the sphere, because every axis that goes to the center mass of the sphere you're going to get the same amount of mr. You're going to get 2/5 mr squared. But if you make your axis parallel to the stick, or you put the axis perpendicular stick, but right through one of the ends of the sticks, like a door. A door, the axis is at one end of the door, not through the center of the door. Okay, you can calculate that. And you're going to get the mass of the door and like the width of the door. You're going to get a W squared and an M, and then like a 1/7 or whatever it happens to be. All right, and it all traces back to this. Now, before we dismiss, I want to give you the right-hand rule. Okay, now this is going to be all pictorial. There's no formula. It's something you've got to mesmerize mentally and using your right hand. All right, so everybody in here's got a right hand, I'm figuring. So what you do is you take if something is spinning, you curve your fingers of your right hand in the sense that it's spinning. And then your thumb of your right hand tells you the direction that the angular velocity, the angular momentum, and the net torque point. We're not close to being dismissed. So don't be packing up your stuff. Now, we're going to use right-hand rule on Thursday when we do the bicycle wheel demonstrations. And let me point out something to you. If you think about it, you're on look at me up here. Everybody look at me up here. I'm riding on a bike. So here's my hands on the handlebars, right? And I'm moving forward. I'm moving out towards. So the wheels are curving like this. And they're coming back around. So the wheels are like that. So my right hand is like this. The angular velocity of the bike wheel, its angular momentum is to the left. If I'm moving straight ahead. Okay? Now, we don't usually back up on a bicycle, but straight ahead, yeah. Momentum's to the left. Angular momentum is to the left. All right? Now, let's take a look at the Orlando Eye. Here's a picture of the Orlando Eye looking to the east, from west to east. And the Orlando Eye, now take your right, now you can do this. Take your right hand and curve it in the same direction. Try to do it without dislocating your arm. Okay, and so your hand is curving over the top. And that means that your thumb is pointing in the direction of the angular velocity, omega. So your thumb is pointing to the east. Now on the screen, the way that you would represent that is with a circle with an X in the middle of it. And the X is to represent the feathers on an arrow that's moving away from you. All right, so here's what I would do. I'd put up there at the hub, that's where I'd put it, I'd put an X. Now, if I have a perspective view, I could make an arrow. But if I'm looking at it face on like this, that's what I would do. All right? Now, behind the Orlando Eye, so here's a guy standing behind the Orlando Eye. He's checking out the shrubbery or whatever, looking for his contact lens. Now, this one, the Orlando Eye is still moving this way, and that omega is pointing towards, same as this one. This omega is pointing towards, like Cocoa Beach or Brevard County or something. Okay, it's pointing to the east. All right? And this one is pointing to the east. But now for him, it's going counterclockwise because he's on the other side of the Orlando Eye. All right? So you'd still sketch in the same omega, even though for him it looks like it's going counterclockwise. And you'd put it up there by the hub. Okay, so here's another look at it. Okay, so here's the Orlando Eye, and there's the angular momentum. Right, and here's the right-hand rule. So my sketch jives with the right-hand rule. All right. Now, let me just, we'll dismiss now. There'll be tiny web courses homework, and look for Chapter 4 mini review. You're dismissed. I'll see you on Thursday.